Hey, hi there. This is Justin Hoffman. I am with Booz Allen in Hamilton, and I'm coming to you from Texas. So I'm happy to be here and presenting to all of you on Spark versus Spark. So that's Spark open source for Spark DBR in an on-prem environment. So as I said, Justin Hoffman, I'm a senior lead data scientist at Booz Allen Hamilton, and I'm going on 9 years at Booz Allen. And also want to say special thanks to the U.S. Air Force for allowing us to collaborate with them and solve real-world hard problems. And also special thanks to Databricks as well for collaborating with us to solve some of our technical problems as we're going through our research. And let's get started. Booz Allen Hamilton has been solving client problems for over 100 years. We're actually at 27,000 employees now, with a revenue of 7 billion for FY20. And what we do at the fundamental level of Booz Allen is consulting services. And we do a lot of technology, a lot of great work for all of our clients to support them in any of their endeavors. And you can see that pie chart there, and where our team sits is within the defense section of national defense. And what I'm going to be talking to you today is one of our client problems where we have been doing research and development in collaboration with them to solve more of a cyber problem using analytics. So 5 of our capabilities at Booz Allen, as I said, fundamentally, we're a consulting firm that was founded by Edwin Booz, and we grew from there to sections like analytics, cyber, digital solutions, and engineering. So what I'm going to talk about is analytics and how it's applied to cyber, and how we support national defense with cyber analysts, and how we're doing that in an on-prem environment with no internet, in enclave environments, and what that looks like, and what a difficult challenge that is sometimes, and how Spark can kind of come through for us. So cyber is a very complex challenge, and it stems that the average intrusion to detection is about 200 days, which is quite a long time in the big scheme of things. But there's a reason why it's such a long time. It's because it's highly complex. There's a lot of data feeds coming from millions of devices. Large corporations have OT, IT, and run-of-the-mill Windows or Linux servers or all those things. All of those are attack surfaces that that are opportunities for adversaries to get into your network. And so suffice it to say, there's a lot of data in cyber as well. And so whenever the cyber analyst is going through all these alerts and looking for adversaries in a network, those things that are anomalies, it actually takes a lot of time and a lot of tradecraft to identify, root source and chase down adversaries in a network. So one thing that we wanted to focus on as part of our research and development is speed. So speed is very important to an analyst. Obviously, whenever you have 200 days on average that you're trying to analyze something, or maybe you are a threat hunter that arrives on mission to find a potential adversary, or just lock down an environment, it's important to have speed, and it's important to have all of the gear that you need in order to successfully do your job. So part of our R&D focused on how do we apply machine learning at scale in an on-prem environment where there's no internet connection, and you have some horsepower there on the hardware, but what does that look like, and is it effective? And oh, by the way, how do we compare that to an open source version of Spark versus the Spark DBR version? And so that's kind of where we have focused here. And there's also been reports out there that some of the nation-state actors, the nation-state adversaries, are getting in and gaining initial access to a computer and pivoting to another computer in less than 20 minutes. And so not only has it gone from 200 days of detection from intrusion to detection, but now in some cases, some of the more sophisticated adversaries can do it in sometimes 20 minutes. So speed is paramount. So this graphic here is kind of I would say, an overview of a data science problem in how Booz Allen kind of looks at the data science process. So we have a bunch of data sources that are from a bunch of different areas of a network. It could be proprietary sources. It could be any data source anywhere. PCAP data, Zeek files, any of those things. And so what we want to do is collect that data, and we want to wrangle it and process it and aggregate it into things that we can understand in a common data framework, common data model, that then we can expose that information by either enriching it or applying machine learning. And ultimately, it arrives at the cyber analyst desk where ideally they have everything at their fingertips, and they can bubble up all of those insights to the very top. And so they can spend the majority of their time on the key things that they need to focus on. So this is more of a higher level process, but I would say 80%, even 90% of our time in any data scientist's time is spent between collection, process, and aggregation. And so whenever you take a look at doing things on premise where terabytes of PCAP is coming off of a network, you have to have a data pipeline that can collect that information and process it, and do so in a rapid amount of time and at scale. And so whenever you get to the expose kind of bubble of this process, that's where machine learning takes place, where it's running on top of Spark or running on top of a distributed cluster, so that you can take your models from local environment to production scale, and hopefully make a huge impact on cybersecurity. So this next slide here, this is a data science framework, data science process applied to a cyber problem. And so just as I was kind of mentioning, you have data coming in from various sensors on the left. You have some sort of data broker there, kind of towards the middle, that is doing some sort of churn of what it means to collect the data, process it, normalize it, enrich it, and then put it into a storage mechanism for later analysis by the analyst. So the normalization engine is a methodology where you have a common data framework, common data model, where any cyber data, you can fit it into some sort of categorization or metadata management of information about the data you're collecting. And so the Joint AI Center has done a really great job about figuring out a common data model for this cyber data. And that model is then impactful for doing machine learning and having proper labels for any enrichment. So during the enrichment phase, we have various machine learning models, because there's not one model to rule them all, if you will. And we apply machine learning on DGA attacks. We can do different random forest models, and we want to apply all of those at scale with the idea that the output or the probability of that recommendation would then give the analyst insight of whether or not that particular method is an indicator of attack or an indicator of compromise. We also have other threat intel feeds that we'd like to add into that enrichment engine, where we can take hashes of different files and send it to something like VirusTotal or any API thing that you could think of, to create a story about all of those endpoints, about the potential initial access for an adversary. And then ultimately, after all that hard work is done, we get down to the analysts, where the analyst then has the hard job of going through and looking through all the different indicators of a compromise, and hopefully has data that's been racked and stacked from top to bottom of the time that they should probably spend at the very, very high likelihood of an attack. And so you can use a bunch of different various tools and that kind of methodology. But that's kind of how Booz Allen thinks about these kinds of things. So as far as our research and development, what we wanted to do is we wanted to go fast. So we wanted to figure out how can we leverage Delta Lake and Spark DBR to kind of cut off a lot of the excess, and if you will, and only prove out that Spark open source and Spark DBR, there's huge optimizations to be gathered there. And I think that's kind of what we've been successful at. So this next graphic here, it kind of shows more of a stripped down version of that process, of more of the research and development process of focusing on leveraging Spark SQL to find IPs that are of interest, and we can we can correlate and gather all sorts of information on that IP using the SQL language that's embedded. And then under the hood, we have Spark open source versus Spark DBR. And the big question there was, does it matter when we move to on-premise whether or not we have Spark open source or Spark DBR? And in fact, it does matter, right? Basically, we have, and we'll get into this later, but DBR does provide large optimizations when doing Spark SQL and looking for different IPs, doing complex joins. And also we get advantages for machine learning as well for whenever we apply machine learning models at scale in an on-premise environment. So I'll talk more at length about Spark, but let's kind of focus on Delta Lake here for a minute. Initially, when we had done our research, we started with Zeek logs that were coming from PCAP data, raw, real data. And we put that into Zeek files. Then we ingested that and put that into Parquet, put Parquet into Hadoop. And then we eventually did the Spark analysis, right? So that was kind of our pipeline. And when working with Databricks, they put us onto the Delta Lake format and all the optimizations possible out of there. And so that really made a lot of sense for us at the Databricks stage, because whenever you have 6 worker nodes and you have a lot of data coming in, I think we had about 1 terabyte or more of data. We wanted to make sure that we were trying to squeeze out as much optimization as possible. And so Delta Lake really provided that, where with DBIO caching and the MariaDB, we were able to get orders of magnitude optimized over the just plain Parquet files. So it's a little bit more cumbersome to work in an on-premise environment than it is in the cloud, if you will. And this really helps to figure out to kind of get you there a lot faster, and to whenever Ethernet cables and gigabit speeds actually matter, whenever deploying VMware containers and virtualized environments, and allocating memory and having to do trade-offs between memory. That's a high-performance computing piece that does actually matter when you're doing on-premise kinds of stuff. And a lot of that is abstracted away for you in the cloud. And so whenever you're running Spark on-premise, it really helps to have a lot of those that knowledge for the trade-offs of what you can or can't do. I think we had iterated quite a few times on how much memory to give each of the worker nodes, how to best to connect things into Hadoop, which it was a great learning experience in all what research and development is for, really. So kind of moving on. we'll explore. So some of the results for Spark open source and Spark DBR. Uh, well, obviously, so in the cloud, we at a minimum can get 5x faster. That picture there on the left was taken from Databricks website themselves, where in the cloud, based upon Spark DBR versus Spark open source on AWS, that at least you get 5x faster. And so, but what does that mean to an on-premise environment? And what does that mean to how to deploy machine learning and do that at scale on an on-premise environment? So there wasn't really a whole lot of, I would say, data out there, at least we felt. So that's kind of what kicked a lot of this question off is, can we do that same thing and get those performance gains that you would see in the cloud in a more closed off enclave on premise? So as you can see on the graph there on the right, biggest performance gains were from the SQL filtering and SQL joins on data that had been parsed, that had been had a model of machine learning applied to the data, and then taking an IP that was of interest, basically replicating what an analyst would do, and using SQL joins to go and find that IP across terabytes or and billions of records is no easy task, right? And so the more complex the join got, the more optimization we got. So a more rudimentary read and count kind of SQL query returned about 4.6x. But whenever we did a filtered count of a SQL, and so we're aggregating maybe two different tables, we're counting, we're doing things, we even saw 43x of return optimization using DBR over the Spark open source version. And so that's groundbreaking to us when doing Spark on premise, because that means that the cyber analysts, whenever they're taking in all these billions of alerts coming from millions of devices, they can now go find an IP and an adversary of threat and get 50x return on optimization if they're using Spark DBR over open source. So that was quite a eye-opening to us and to the clients we support. And one of the things that I wanted to mention here, we see decision tree here is not really a whole lot of optimization there. One of the things that I wanted to mention is that there are probably better ways that we could have coded on some of the machine learning pieces too. So there's like ML flow that we have, that's part of our future work, and having user-defined functions executed properly within our own machine learning model to make sure that we can even boost up those performance gains on DBR whenever we're performing the machine learning at scale. So if you can kind of see there, a billion records or more, 43x in return if you choose to go with Spark DBR for an on-premise deployment. And it is possible to deploy DBR on-premise, and you don't have to necessarily use open source Spark. So some of the lessons learned that I wanted to get into, we have so Spark DBR and Delta Lake, obvious up to 50x depending on what kind of join you're doing. Really important for the analyst and an IP of interest. So whenever we did neural network classification with DBR, we were still able to see a little bit more than 4x. And if we in the future work, whenever we deploy our neural networks, we'll make sure that we're doing it kind of in an optimized method. But really exciting to see deep learning deployed on premise on Spark and doing it on real client data. So we also experienced some open source some failures from the worker nodes. So initially we thought it was Spark open source that was failing when some of our big data jobs wouldn't finish, but it turned out that it was our distribution of Hadoop. And so lesson learned there is to also check your Hadoop distribution and maybe use a different type of distribution that is more maintained by open source community. And that way maybe you won't experience worker nodes just dying off and not completing jobs. We also thought that leveraging data lake in the format with Parquet and Maria was key as well, because you definitely get more optimization over any of the RDDs, and that opens a lot more research for us for how do we ingest data at scale, and how do we do it streaming to provide the best possible user interface for any of the cyber analysts and enable our partners to threat hunt effectively. So look forward to all of your questions, and again, thanks for attending this talk, and have a great one.